Okay, this lesson covers our intermolecular forces that was covered in class today. Let's describe each type of intermolecular force and how it will relate to a simulation that I provided for you as well. The first type is the weakest. It's called dispersion or London dispersion forces. All molecules and atoms have this. Especially reserved, though, for a nonpolar molecule. A nonpolar molecule has very little interactions. There's no charges. So it's a very quick interaction between molecules that doesn't tie them up at all, very much at all. So since they're so weak, they're called dispersion forces. We get slight pluses and minuses in the molecules that temporarily exist, and they're not there very long at all. Okay, and that's what the molecular interaction is for nonpolar molecules. The next stronger are dipole-dipoles. These are for polar molecules. A dipole means two poles. We have a plus in the molecule and a minus in the molecule. If we take a look at this example here, we have a plus on this side of the molecule and a minus over here. Now remember, these are intermolecular forces. So the negative of this molecule here will be attracted to the positive of this molecule over here, and vice versa. So that's why they're called dipole-dipole. This is a dipole, a polar molecule, attracted to another polar molecule, which is a dipole. Now hydrogen bonding is just a special case of dipole-dipole. Why is it called hydrogen bonding? Well, first of all, it's a hydrogen atom bonded to either a fluorine, oxygen, or nitrogen. Water is a very good example of that. There are two hydrogens bonded to an oxygen. That makes really large plus and minus charges in this molecule. And then they interact with each other. The positive of this hydrogen on this water is attracted to the negative of that oxygen on that water. And vice versa, all over the place, these attractions exist. So that's why it's called hydrogen bonding, because it involves a hydrogen atom, which is really positively charged, attracting to the negative part of another atom, of another water molecule. And then lastly, the strongest of the interactions are mixtures of ionic compounds and polar compounds, like salt and water, for instance. It's an ion dipole. Let's say this positive here is sodium plus. It'll be attracted to the negative of water, and that's why it's called an ion, to a dipole. Dipole because this is a polar molecule with a plus and minus charge. Very, very strong interactions. That's how sodium chloride can dissolve into water. All right, let's take a look at assimilation. I want to show you this. Let's take a look at salt and water. So we have sodium and chlorine in crystal form. We're going to watch the ion dipoles react together. This is the ion, that's a dipole. The negative of oxygen will be attracted to the positive of sodium, and the negative of chlorine will be attracted to the positive of water. Let's hit start and see what happens. Okay, see how strong the interaction is between the ion and the dipole? It's able to split apart the sodium chloride crystal and dissolve it and mix it around all with the water. That is ion dipole, the strongest of the intermolecular forces. Let's do next. We'll do a simulation between alcohol and water. Water is a polar molecule, so is alcohol. Alcohol does contain some tetrahedral carbons in it, but it has this bent shape right here. Notice how we have hydrogen attached to oxygen again, and hydrogen attached to oxygen. So this can cause hydrogen bonding, the strongest of the dipole-dipole interactions. Let me hit start here. And we see that water will mix with alcohol. Alcohol dissolves in water and vice versa. Why is that so? Well, we have a hydrogen bond between this hydrogen atom and this oxygen. A negative and a plus attract. We have a hydrogen bond between this plus hydrogen and that negative oxygen over there. So remember, hydrogen bonds are just a special kind of dipole-dipole interactions. Anytime you have pluses and minuses interacting with each other in covalent molecules, it's called dipole-dipole. Okay? Let's do another example. Let's take the alcohol and see if they could separate out sodium chloride. Let's see what happens. Let me hit start on that. Okay, we see that it can't do it. Okay, we have to remember that sodium and chlorine are also attracted to each other. Water is polar enough, strong enough to break apart the sodium chloride bond, but alcohol is not, because we have this polar molecule here, this part, with a non-polar carbons in there. These are tetrahedral carbons with no lone pairs. So we find that salts won't dissolve in everybody because they're still ionic and attracted to each other. You've got to have a really polar solvent like water oftentimes to dissolve these sodium chloride and other ionic bonds together. So I want to point out your polarity can be limited if you put nonpolar parts on your molecules. Okay, now let's do a straight up nonpolar. Okay, what about a molecule like this? It contains a whole bunch of carbons in it. The name of this is, let's count the carbons. 1, 2, 3, 4, 5, 6, 7, 8. This is octane. Okay, octane, usually it's branched, but octane is in gasoline. Okay, but here we go. This is a nonpolar molecule. All of these carbons and hydrogens are completely symmetrical. There are no lone pairs. There's very little charges on this. Here's our polar water. Let's see what happens. We hit start. Water tries, but it ends up bonding with itself instead because this plus is attracted to this minus over there by hydrogen bonds. There was nothing on this molecule here to attract the charges of water. Again, this is a nonpolar molecule. It has London dispersion forces, very, very, very weak interactions. So water sticks to itself and does not interact with the water or with the octane here, okay? That's the reason why oil and water don't mix. Oil is a very nonpolar molecule. It will not mix with water either. Okay, now what about our last one? Soap. Okay, soaps in general look like this. They have a carbon tail that's very nonpolar, and then they have a part that's really, really polar, sulfur and oxygen here. This is sodium dodecosulfate. This is what's in Dawn. Okay, so what if I have water, alcohol, and this octane molecule? When I hit start, we're going to see that they all come together. The oil is attracted to this nonpolar part, so this nonpolar will mix really well with this nonpolar by those weak interactions. The polar molecule of alcohol will be attracted to the polar end, and this water molecule here will also be attracted to the polar. And this is how soaps work. You want soap, this tail, to dissolve in the oil and dirt and grime in your clothes, let's say, and you want this to dissolve with water so that you can rinse all of that away. So when this gets carried away with the water, it carries the dirt and oil and grime or whatever it is you were trying to clean off. And that's how soaps work. Soaps kind of get along with everybody then. They mix with both polar and nonpolar. Why? Because they have a nonpolar part and they have a very strongly polar part. Okay, and that's our lesson today on intermolecular forces.